Today we have discussed about this part, right? So about the solid, liquids, and gas, and the states of matter, right? So actually, you already know about these things, right? You must have learned in chemistry as well, right? But we have to brief about this thing, right? Now we know when it comes to matter, right? So there are three states, right? So which are known as solid, liquid, and gas, right? Now, what do you know about solids? What do you know about liquids? And what do you know about gases? Hmm. Yeah, correct. Yeah. Hmm. Hmm. Yeah, correct. Right. Now, so then, yeah, since you know these things, right? So I'm not going to go into details, but we'll just make a note because these things they ask regularly in exams, right? Now, solids, right? Yes, if you take the particles, right? So then, solid particles are arranged like this, very close to each other, right? So in this kind of arrangement will be there, right? So particles arranged like this. So then we normally say it's a regular arranged particles, right? Regularly arranged, right? And we can say they are also tightly packed, right? And what can you say about the shape and volume? Is that has a constant shape? I mean the definite shape and definite volume, or it is changing? Yeah, definite shape and definite volume both are there. Definite shape and definite volume is there, right? And why is this kind of tightly packing is there, right? So regularly packing is there because these particles they are connected by very strong attraction forces, right? So we normally say there are very strong intermolecular forces they are between particles, so that's why these particles are tightly packed, right? So then strong intermolecular strong molecular intermolecular forces between the particles, right? And also we can say now when it comes to solids, right? So it is not much easy to expand or compress, right? So we can say it's difficult to expand and compress, right? So that's the nature of solid, right? Then when it comes to liquids, right? So liquid particles are not so tightly packed, right? So they are closer to each other, right? So it's not so regularly arranged. Some particles may be closer, some particles may be moving away, right? So, but relatively closer, right? So then there is no, I mean, it's not so regularly arranged, right? Or not regular or irregularly arranged, right? We say irregularly arranged, right? So then they are not so tightly packed, right? Not packed tightly. One more thing we forgot to mention. Oh, sorry, we'll come back to that one, right? So we know the liquid particles, so they can move over each other, right? So then particles move over each other, right? So what kind of motion are there for solid particles? How are the solid particles are vibrating? I said the word, it's vibrating, right? Solid particles vibrate around a fixed position. Solid particles are vibrating around a fixed position while the liquid particles can move over each other, right? So then when it comes to liquids, there is a definite volume is there, but the shape, they take the container's shape. Take the shape of container, right? But it has a definite volume, right? And when it comes to intermolecular forces, right? So these intermolecular forces between the liquid particles are not so strong as solids, right? But there are some intermolecular forces. So then we can say there are intermolecular forces which are weaker compared to the solids, right? Intermolecular forces are weaker than solids, right? And these liquids relatively easy to expand and compress compared to the solids, right? uh, Easy to expand or compress than solids. Okay, right. Before we go on to the gases, just mention these points with the figure, because this figure sometimes they ask you to draw the figures. This is a solid, this is a liquid. Then gases, right? So when it comes to gases, right? So gas particles are not bound at all, right? So then gas particles are random. They are not so close at all, right? So particles are not arranged at all, right? So then these gas particles can move randomly in different directions, different speeds as they want, right? Particles move randomly, right? And when it comes to gases, right? So there is no specific volume or shape, definite volume or shape, right? It takes the volume and shape of the container it's placed in, right? If it is in a room, the room's volume is the volume of the gas, and the shape of the gas is also the volume of the room of shape of the room, right? It takes shape and volume of the container, right? So then when it comes to gases, right, so they are moving randomly because they have very low or no intermolecular forces at all, right? Normally we say the intermolecular forces. There are no intermolecular forces, right? And they are easy to compress or expand, right? Right, this one as well. Right, so just keep these properties in memory because they time to time they are asking about these properties regularly, right? Now next part is about conversion between these states, right? I'll go to the board, right? Now we have the three states: solids, liquids, and gases, right? Now if you want to convert a solid into a liquid, what do you have to do? Melt. Yeah, that is what happening, right? So how do you melt something? By heating, right? So heating means we have to supply thermal energy, right? So for this process to happen, the supply thermal energy, right? So then solid to liquid conversion we call it as melting, right? So then if you want to convert a liquid into gas, we have to do the same thing. That means we have to continue to supply thermal energy, right? So this process is known as what? Liquid to gas conversion. No, evaporation is separate one. Boiling, right? So liquid to gas conversion is called boiling, and if you convert liquid into solid, what do you call that? That is freezing, right? How do you freeze something? Don't say put it in the fridge. Decrease in the temperature means you are removing the thermal energy, right? So we are removing thermal energy, right? So for heating, what we do is we supply thermal energy. For melting, right? For freezing, we have to remove the thermal energy. When you put something in the refrigerator, right, cools down means it is losing its thermal energy, right? Now last week also we discussed when we supply thermal energy to something, the temperature increases. When you remove the thermal energy from something, the temperature is decreasing, right? So then when it reach a certain temperature, it starts to freezing. And what is this process is called? Gas to liquid, gas to liquid condensation, right? Condensation or condensing, right? In this one also, we have to remove the thermal energy. Okay. Normally, we know when it comes to water, right? So water mean ice converting into liquid, or liquid water converting it into ice, right? So that's happening at 0 celsius, right? So that temperature we call it as freezing point or the melting point. Melting or freezing point, right? And when something is converting, right, so into liquid into gas, so gas into liquid, that is normally happening for water at 100 celsius. So this point, this temperature is we call it as boiling point, but we don't say it as a condensing point or anything, right? It's just a boiling point, but even if you say it is as boiling, right, it's not 100% wrong. Okay. And but if you check your note, right, so in that figure here, it's mentioned that evaporating, right? So then you just have to correct it into boiling. Okay. Evaporation is when separate thing. I'll explain what is meant by evaporation, right? So there's a main difference is there, right? Okay, clear, right? Right. Now, now one thing what we're going to discuss is, right, so the energy changes involved, right? So that means when you are converting something into this kind of state change, right? So whether it's solid to liquid or liquid to gas, right? Some of the energies involved, right? Whether we have to supply energy or whether we have to remove the energy, right? Now keep in mind, right? So let's say we have a solid, we have ice, right? Let's say ice at temperature of minus 10 celsius. I want to convert this into water at 25 celsius temperature. Okay, right? So then if you take ice cubes from the fridge, right? So then this is now at minus 10. What do you have to do? We have to supply the thermal energy, right? So when the thermal energy is supplying, right, so first thing what happens is this ice goes from minus 10 to 0 celsius, right? So once it reaches the 0 celsius, what will happen? So then the melting starts. Okay, so during the melting starting, right, so until all of these ice particles completely converted into water, the temperature remains at 0 celsius, right? So we are now another example. Let's say we have some, wax, candle wax, right? So in normal room temperature, the candle wax is at the solid state, right? If you take some candle wax like this and if you pour it into some sort of beaker or something, right? Now this is, let's say we melt it and pour it, so then after a while it gets cooled down, it gets solidifies, right? So then when it solidifies, what happens is, right, now in the room temperature, the wax is existing as a solid state, right? Now let's say we are supplying thermal energy from below, right, using Bunsen burner or a candle or anything, right? So the thermal energy is supplied from below, and let's say we have a thermometer inside it, so then we can measure the temperature of the candle as the temperature rises, right? And if you draw the graph between the temperature with the time, temperature in Celsius, and on this axis, let's say we have time in seconds, right? So then starting from room temperature, right, let's say 25 celsius or something. So when the solid wax is given thermal energy, the temperature of the solid wax is increasing like this. Okay, so as soon as it reaches the melting point of the solid wax, right, so remember, even though you supply the thermal energy, right, the temperature remains constant like this, right? So why is that? Because even though we are supplying thermal energy here, right, whatever thermal energy we are supplied here is used to break the bonds between, I mean, like loosen the bonds between the solid particles, right? Now here what is happening? A solid to liquid conversion is happening, right? Now remember we discussed in a solid there are very strong intermolecular forces between the particles, right? So then when it comes to liquids, the strong molecular forces are no longer strong, right? So the intermolecular forces are weak, right? So therefore, to reduce the strength of those intermolecular forces, right, so we have to supply thermal energy. When the energy is supplied, what's happening is the particles, the bonds between the particles will be, some of it will be completely broken, some of it will be reduced, right? So that's why the particles in the solids when it converts into liquid, the particles can move more freely compared to a solid. Is it understood? Right? So then if you have a solid here, right, when you're supplying thermal energy, solid's temperature is increasing, right? So once the solids begin to convert into liquid, the temperature remains same, and once all the solid particles have completely converted into the liquid state, right, so then the temperature of the liquid will rise like this, right? So then this is what I was trying to mention here. If the temperature variation of the solid is heated above its melting point, right? So we are supplying the thermal energy to something, right? So then above the melting point, we are heating some material, some solid material, right? So the graph would look like the following. Means the same graph, just I just drew it there, right? It looks like this. Temperature maybe in Celsius, time in seconds or in minutes, right? So starting like this, draw this graph there. After that, label these sections. This is the solid state. So then this is the solid plus liquid is there. In this part we have only liquid. Uh, this is what explanation, right? So temperature of the solid rises until it starts to melt, right? So from whatever the initial temperature, right, until its melting point, it reaches the temperature is rising. Until all the solid has melted, its temperature remains constant, right? The temperature will start to rise again when all the solid converts to liquid state. Then the thermal energy supplied is used to overcome the forces between the molecules of the solid. During the state transition. During the state transformation, the temperature, whatever the thermal energy we are supplied, is used to overcome the whatever the attraction forces between the molecules in solid. Okay, right now one more thing, right? So sometimes now at this O levels, right? So it is okay to draw this one as straight line. Sometimes you might see this one is drawn like curves like this, the first and the last part. Sometimes it can be drawn a curve like this. So then you don't have, even if you draw it like curves, no problem at all. But at our level, right? So we can just draw it as a straight line. Okay. And if you allow the liquid to cool down, right, now we converted the solid into liquid, right? So then we are allowing it to cool down, right? So then before it reaches the thermal, I mean the temperature of the room temperature, right? So then the mm, once again it will go through the freezing, right? So then once again it goes through the melting point or the freezing point, right? So therefore the liquids will be converting into the solid, right? So then if you measure the temperature again, right, you might see a graph like this, starting from some high temperature, right, reduces until it reaches the boiling, sorry, the freezing point. So then it remains constant, and the last part it going down again, right? So now this temperatures will be the right? So most important thing is during any state change, melting or freezing, boiling or condensing, the temperature remains constant, right? So draw that graph there also. Label the axis. This is temperature. This is time. And this graph does not come to zero. It may or may not come to zero. Depends on the type of material that we are using. If you check this question, this is from past paper actually, right? I can't remember exactly which year. So diagram shows the temperature time graph for a substance which is heated at a constant rate. Which section of the graph shows when the substance is melting? What do you think? B? Yeah, answer B. Yeah, QR section, right? So then we can assume now here what is happening, right? There are more than one state transition happening, right? You can see here one state transition happened, there's another one state transition happened. So then which one is happening at the low temperature? That is the solid to liquid conversion, right? So then this is solid to liquid conversion. So then this is liquid to gas conversion is happening, yeah, right? So therefore QR is the answer, right? Next one, which section of the graph shows when all the substance is solid? A, yeah, correct, right? So this is the solid part. It means PQ. So here it says draw particles in the box to show the arrangement of particles when the substance is gas, right? So in this kind of situation, what do you draw? Draw particles randomly, right? Few particles, not closer at all, right? So then randomly draw, right? Next one, which of these statements best describe the motion of particles in gas? Yeah, they move quickly and randomly. Um, name a piece of apparatus that could be used to measure the temperature of substance. Thermometer. Determine the boiling point of this substance. Now that one again you had to use the graph. What could be the boiling point of the substance? 80. Yeah. So then this is the liquid to gas conversion. So we can. It looks like it is coming happen. It's happening at 80. Yeah. And this part is related to the topic we discussed last time as determine the substance has a mass of 1.2. Calculate the energy required to raise the temperature of the substance from 10 to 37. We know energy equals mc delta theta. Mass is 1.2. Specific heat capacity is 840. Temperature change is from 37 minus 70. Okay. Okay, that's it about the state transition, right? So then just keep in mind the basic properties of the solid liquids and gases, right? So and how the state transition is happening, just keep that in mind, right? And just give what is meant by evaporation, right? It says when liquid particles on the surface receive enough energy from the surrounding, they can escape into the gas state even below the boiling point. Energy is absorbed from the surrounding particles. This is called evaporation, right? Now, uh, normally boiling is happening at boiling point only, right? Now if you have the water, right, so if you want to boil water you have to rise, you have to increase the temperature up to 100 celsius, right? So in that case the liquid converts into gas is happening, no problem at all. But we know if you spill some water on the floor or a table, right? So then after few minutes or after about an hour, right, so all those spilled water will be gone, right? So this is what we call as evaporation, right? So then boiling is happening at this 100 Celsius temperature, but evaporation means it can happen at any temperature, even below the boiling point, right? So that's normally how the drying of the water happens. Water or any liquid can be happening, right? Generally this is now even when you know when you wash your clothes and when they were put dry, right, so that drying is also evaporation, right? So there what happens is if you have a liquid water is there, right, let's say container or anything, right? So now what happens is the particles on the surface, right, so only from the surface, right, so that's what it say when the liquid particles on the surface, right, so they can absorb the energy from the surrounding and they will jump into the gas state, right? So now if you want to jump into the gas state, so this liquid particle has to break whatever the existing bonds with the surrounding particles, outside particles. So then that to break that bond, right, so the energy will be absorbed by the surrounding as well, right? So maybe from the neighboring particles and also sometimes from the atmosphere as well, right? So once this water particle absorb enough energy, what will happen, it can break the bonds and it can escape into the atmosphere, right? So therefore this evaporation is happening only from the surface. Is it understood? Right, so that's what mentioned here, right? So they can escape into the gas state even below the boiling point. Energy is absorbed from the surrounding particles. So then this is called the evaporation, right? Now if you want to increase the evaporation, what can we do? Can you give me any method of how to increase the rate of evaporation? And let's say you spill some water, right? So then if you want to dry that water quickly, what can you do? That is removing artificial, right? Yeah, that's correct, right? So then, if you have the water within this kind of region, right? So maybe if it is in the ground, right? So it maybe with a wiper or something, or maybe using your foot, right? So we can spread this water through a large area. So then, what will happen when you spread this water in a large area? What will happen is, now I told you the evaporation is happening only from the surface, right? So when you spread it, what will happen? There are more particles within this large area, surface area, right? In the first situation, the area is small, so that means only few particles are on the surface. In this case, we have more particles on the surface, so then there are more particles can escape into the gas state. Okay, so then one thing you can do is we can increase the surface area. Anything else? Correct. Yes. Temperature, right? If you can increase the temperature, right? Now, let's say if you want to dry something quickly, right? You can keep it near a fireplace, right? Oh, then what will happen when the temperature is supplied? This temperature means we are supplying thermal energy, right? So energy is supplied means the particles on the surface gets more energy means they can escape into the atmosphere quickly, right? Now, normally what they have to do is they have to absorb the energy from the surrounding particles, but that might take some while, right? But when you supply thermal energy, more particles will have enough kinetic energy, so then more particles will jump into the atmosphere, right? One more thing that you can do. What will you do? This one is normally we do during rainy days if you want to dry our clothes quickly. That is, sorry, what did you? I didn't hear you. Wind, yes, correct, right? So when in rainy days, right, we put our clothes somewhere on a table or somewhere, right? So then we keep the fan on, right? So then what happens is, right? Now let's say we have the water like this, water surface. So then most of the time, whatever the particles escaped in the atmosphere, they will like remaining in here in the space above, right? So when there are more particles here, right? So then the number of particles that can evaporate is is getting less when the more particles are remaining above the liquid. So that is why now during the rainy days the atmosphere has more moisture particles, more water particles, right? More gas, moisture particles. So that's why it is difficult to dry our clothes during rainy days, right? So the water is not evaporating in the same rate as it done in a normal dry days, right? So then if the air particles are remaining there, not the air particles, the moisture particles are remaining above the water surface, so then there is less chance for the remaining other liquid particles to convert into the gas state, right? So when you have a wind, right, if there is a wind blow, right, that means if there is a fan or something, what will happen is these particles will be removed, right? So once they remove, they are, yeah, above this region will be dry, more drier, right? If the air is drier, so then the particles can absorb. That means particles can jump into the gas state much better, right? So therefore, those are the things that we can do to increase the rate of evaporation, right? One thing you can do is we can increase the temperature. So then what happens? More particles. We can write this one down. Enough kinetic energy to escape, right? And second method is increase the surface area. In more particles, third one, blow wind. mention those. Right. So then when it comes to evaporation and boiling, right? So this also they had asked in exams, right? What are the difference between the boiling and evaporation? Boiling, evaporation. What can you say? Source of heat. Right. So that's true, but mm, even evaporation can be also be done by uh, constant rate of heat. If you supply the heat, yeah, but it require energy. No, somehow we have evaporation also require energy, right? Now, how do we, the supplying energy is the only difference is there, right? So evaporation, the energy is supplied by the surrounding particles. Boiling energy is supplied from outside. Yeah, you can say like this. Huh. Uh, yeah, so for boiling, what we can say is we have to supply energy from externally, right? Supply energy externally, right? So evaporation, energy is absorbed from surrounding. Okay. What else you can say? What about the temperature? Now the boiling is happening only at a specific temperature, right? Right. So happening only at, this is only at boiling point, right? But the evaporation can happen at any point, any temperature. Right? So now maybe that energy thing you can write later if you haven't written, right? So then these ones are more important, right? So the temperature, main differences, right, can happen at any temperature and only from boiling point, right? So and boiling happening all through the liquid, right? When you are boiling the liquid, right? So the water converts into liquid from any point of the liquid, right? It could be from the bottom, it could be in the middle, it could be in the surface, but the evaporation is happening only from the surface, right? Happens anywhere in the liquid, but this one evaporation occurs only from the, only at the surface, right? And when during boiling, right, we can see bubbles, we can see bubbles forming, yeah, bubbles, but in the evaporation, no bubbles. Okay, right, just mention those points as well.